Our lesson today is understanding tiling in rectangles. Let's begin. The objectives for this lesson: analyze tiling as an array of squares with no gaps or overlaps. Determine the number of squares used to tile a rectangle. And create a tiling of squares to fit a rectangular shape. Our vocabulary this week is all review, so these are terms you've seen before. The first term is array, a set of objects arranged in equal rows and equal columns. Row, the horizontal moving across left to right, the horizontal groups of objects in an array. And column, the vertical or up and down groups of objects in an array. Here's an example of an array that we have two rows, 1, 2, and 3 columns, 1, 2, 3, in this array. I want to review a concept about shapes from a previous lesson. That is, that shapes can be composed of other shapes, triangles to make a square, such as in these two squares. You can see we use triangles to create them. We can combine a square and a triangle, for example, to make a pentagon, such as we did down here. It kind of looks like a house. I also want to review the attributes of rectangles and squares. Rectangles and squares are both quadrilaterals. That is, they are two-dimensional closed shapes with exactly 4 sides and 4 angles. A rectangle has 4 sides and 4 angles. It has 4 square corners, think of the letter L, and opposite sides that are the same length. By opposite sides, we mean top and bottom, and left and right. So you can see that even though the left and the right are much shorter on this green rectangle, that they match each other. We'll also be working with squares. A square is a quadrilateral. It's also a rectangle. So, like a rectangle, it has 4 sides. It has 4 square corners. And the opposite sides are the same length, but in the case of the square, all 4 sides are the same length. So it is the same length, top and bottom, as well as on the right and the left. You can put squares together to make a rectangle. You can put 12 squares in one row to make a rectangle. It makes a very long, skinny rectangle. And to count those squares, you would just count by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You could also put them in 2 rows to make a rectangle. You still have 12 squares, but now they are arranged in 2 rows of 6. So 6 squares in the top row and 6 squares in the bottom row. Make a drawing with 12 squares where there are 3 rows. So we looked at one where there were 12 squares in one row, and then 12 squares across 2 rows, 6 top and bottom. Make one, use pen and paper, where there are 3 rows. How many squares would be in each row? Here you see what that might look like. There are 3 rows of squares. 1, 2, 3. There are 4 squares in each row. That means that there are 4 columns. 1, 2, 3, 4. Making a rectangle in this way is like covering a rectangle in squares with no overlaps or gaps. I hope that you are beginning to see that this tiling or arranging of squares looks like an array because the squares are lined up in rows and columns. If I remove a square, is this still a rectangle? Is it still an array? No, it's a hexagon now, right? It's got 1, 2, 3, 4, 5, 6 sides, and 1, 2, 3, 4, 5, 6 angles. It's also no longer an array because an array must have the same number of objects in each row and column. Arrays made by tiling use. The pictures on the left are arrays because they use same-sized squares within each picture. So this one uses 3 large squares. This one uses 2 rows of 6 squares that are smaller, but they're all the same size. So this is an array. This is also an array. The pictures on the right are not arrays. And it's a little tough to see because they put it on grid paper, but you can see that this one uses 2 big squares on the top and 4 little squares on the bottom. So all the squares must be the same size. On the right, you have 2 big squares on the top, and then these are actually rectangles on the bottom. So the reason why that's important is that this concept of tiling, it helps us to understand arrays, which leads to multiplication in algebra, but it also leads to finding areas of spaces, rectangular spaces in geometry. So you really want to get into this habit of looking for the same size squares because it's going to allow you to figure out how many squares you need to cover that space. You can represent the arrangement of an array with an equation. This one would be 4 plus 4 plus 4 equals 12, right? I'm adding up the squares in each row. You could also represent this with 3 times 4 equals 12. I tend to create equations using rows rather than columns. The columns is correct, but kids tend to get confused. So why not make it as easy on ourselves as possible? We'll be consistent, right? Let's practice. Tim says there are 9 squares in this rectangle. Do you agree? No, the shapes in the middle are rectangles and not squares. Let's practice more. How many rows are in this rectangle? There are 6 rows in this rectangle. Let's count. 1, 2, 3, 4, 5, 6. How many columns are in this rectangle? There are 3 columns. Let's count. 1, 2, 3. Write an equation to represent the number of squares in this rectangle. You can create a repeated addition equation, such as 3 plus 3 plus 3 plus 3 plus 3 plus 3 equals 18. It's a very long equation. Or a multiplication equation, such as 3 times 6 equals 18, right? Because there are 6 threes. 1, 2, 3, 4, 5, 6. That's where that comes from. Now, as I said before, you could also create your repeated addition or multiplication equation based on columns, and it would still come out to 18. I just tend not to do it that way, but it's not wrong. If that's how you see this rectangle, then go ahead. Just be consistent with whatever method you choose. The size of the squares impacts how many will fit. Think about this. Molly and Nina paste squares on posters that are the same size. Who will use more squares to fill her poster, and why? Molly will use more squares. Here's Molly's square. Each square is smaller as compared to Nina's, so Molly will need more squares to fill the same amount of space. Here's another practice problem. 3 centimeter square tiles will Sue need to fill her mosaic. The mosaic is 12 centimeters tall by 24 centimeters wide. Here's a hint. We know that each square is 3 centimeters across and down. 3 is a factor of 12. 3 times 4 equals 12. 3 is also a factor of 24. 3 times 8 equals 24. Sue will need 32 3 centimeter tiles. She'll end up with 4 rows, 1, 2, 3, 4, and 8 columns, 1, 2, 3, 4, 5, 6, 7, 8. In other words, 8 plus 8 plus 8 plus 8 equals 32, or 4 times 8 equals 32. What if she uses 4 centimeter square tiles? How many will she need to fill her mosaic? Here's your hint. Each square is 4 centimeters across and down. 4 is a factor of 12. 4 times 3 equals 12. 4 is also a factor of 24. 4 times 6 equals 24. Sue will use 18 4 centimeter tiles. She'll end up with 3 rows and 6 columns. Here's 1, 2, 3 rows and 6 columns. 1, 2, 3, 4, 5, 6. An equation to represent this tiled array is 6 plus 6 plus 6 equals 18, or 3 times 6 equals 18. What happens if you only have, or if Sue only has, 5 centimeter squares? This is a little bit more difficult. Here's your hint. Is 5 a factor of 12 and of 24? No, it's not. Here are the factors of 12. Here are the factors of 24. And you can see that those two numbers share many of the same factors. But 5 is not one of them. Therefore, 5 centimeter squares won't fit evenly on a 12 by 24 rectangle. What we learned in this lesson: to analyze tiling as an array of squares with no gaps or overlaps, determine the number of squares used to tile a rectangle, and to create a tiling of squares to fit a rectangular shape. I hope this was helpful. I'll see you in class.